We present a method for computational modeling and macromechanical characterization of discrete interlocking materials, generalized chainmail fabrics made of rigid elements. Unlike conventional elastic media, the mechanics of discrete interlocking materials are governed by contacts between individual elements. These contacts give rise to deformation constraints for in- and out-of-plane motion. The corresponding limits can vary strongly with direction and exhibit complex coupling between deformation modes. For example, this three-fold symmetric chainmail shows an interesting saddle shape when bending it along a given direction. This torus knot structure admits large cylindrical bending in two orthogonal directions but prefers spherical curvature when bent along its diagonal. This scale mail material shows completely different bending limits for positive and negative curvature. While deformation limits are determined by the shape of, and connectivity among, their elements, predicting the macromechanical properties of discrete interlocking materials from their native structure is a highly non-trivial task. In this work, we propose a computational approach for modeling and characterizing discrete interlocking materials. Our method builds on three main components: native scale simulation model, data generation and strain space construction, and macromechanical simulation. We start by building a native scale model based on rigid body simulation with contact in order to determine the macroscopic deformation limits. For each material, we perform thousands of virtual deformation tests for uni- and bi-axial stretching and bending in different directions. We use these tests to explore the set of feasible deformations in strain space and construct an explicit representation of its boundary. We then use this strain space boundary to build a macromechanical model for discrete interlocking materials that combines thin shell simulation with homogenized deformation constraints. We applied our method to a range of discrete interlocking materials with different element shapes and connectivities. Our first example is a hexagonal pattern in which each element connects to its 6 immediate neighbors, leading to an overall threefold symmetric structure. For the in-plane uniaxial strain, we obtain an almost isotropic limit profile with only small fluctuations. The out-of-plane profiles are also almost isotropic. However, the difference in sign between principal and orthogonal limits suggests a rather interesting behavior. When applying uniaxial bending in any given direction, the material will bend with opposite curvature in the orthogonal direction, leading to characteristic saddle shapes. To validate the results obtained through simulation, we fabricate prototype samples using 3D printing. We generally obtain very good agreement between predictions and actual deformation limits for in-plane behavior. Our experimental setup for bending uses a linear stage for controlled deformation and optical marker-based tracking for deformation capture. We load the pre-bent sample in a given direction such as to gradually increase its curvature. We stop once the force sensor signals that a threshold value has been reached, indicating the deformation limit. We then reconstruct the curvature from the captured data. This process is repeated several times for different bending directions. The measured deformation limits are overall in good agreement with our predicted profiles, indicating almost isotropic bending limits for this threefold symmetric structure. We further compare our macro-scale simulation results with native-scale simulations and deformations observed in physical prototypes. The macro scale successfully reproduces the saddle-shaped deformations when subject to uniaxial loading. It also shows good agreement with native-scale simulations and the physical prototype. Our second example is a four-fold symmetric material consisting of torus knot elements arranged in a regular quadrilateral grid. This material likewise shows an almost isotropic in-plane behavior. Compared the three-fold symmetric chainmail material, however, it exhibits a much smaller range of motion. The bending behavior is much more interesting in comparison, showing large limits in 10 and 100 degrees, but much tighter thresholds in 45 degrees. This behavior is also readily identified in the strain space boundary for bending, which shows star-shaped protrusions. Our macromechanical model again closely approximates the behavior observed in native-scale simulations. As shown in this example, our method can be applied to elements with more complex geometry. Here the element consists of a 6-fold symmetric base with a hexagonal plate on top of one side. Although the bending profiles show somewhat larger deviations from the measurements, Our macro-scale simulation results again closely track the behavior observed in both native-scale simulations and physical prototypes. The asymmetry in the shape of this material translates into an asymmetric bending behavior. As can be seen from this example, in one direction, the bending limit is determined through contact between the interlocking rings and the base. In the opposite direction, contact between the scales puts a much earlier stop to bending. Thank you.